Hello students, today we will start the chapter number 2, that is electrostatic potential and capacitance. Electrostatic potential is the amount of potential which is contained by the electrons at static position, and the capacitance will be learnt later on. The capacitance is the amount of energy that is being stored by the device known as capacitor. How these devices are made and what is the mechanism behind the storage of energy in the capacitor is what we will read under the topic of capacitance. So let's start with the electrostatic potential. In the previous class, in your class 11, you have read the chapter work, energy, power, chapter number 6, and the other chapter, that is gravitation. So in these both the chapters you have seen the concept of energies. In that we have many kind of energies, but mainly the energy we focused were kinetic energy and the potential energy. So what is kinetic energy? The energy with the virtue of object speed is known as kinetic energy. Kinetic energy present in an object due to virtue of its velocity is known as kinetic energy. It is given as half mv square in general, and the potential energy is defined as energy present due to the virtue of position or height. So potential energy is given as mgh, where mass is the mass of object, g is the gravitational acceleration, and h is the height. So total energy of a system is potential energy plus kinetic energy in any system is conserved. The amount of potential energy and kinetic energy can be interchangeable. If kinetic energy is increasing, then the potential energy will decrease, but the sum total of these two energies will remain equal always, will be conserved or will be constant. This particular statement comes from the law of conservation of energy. Law of conservation of energy. So where we can see these potential energies and kinetic energies, we will read out some examples like external force does work in taking a body from a point to another against a force like spring force or gravitational force. That work gets stored as potential energy of the body. Like in this spring you have seen, this is our spring connected with a mass m. So if this mass is able to displace the spring by x, we give its kinetic energy as half k x square, whereas this potential energy is given as spring constant into the acceleration and the displacement. So when the external force is removed, the body gaining kinetic energy and losing an equal amount of potential energy. Now in this spring, this external force, this mass is removed. What will happen? Spring will try to restore its position. For restoring, whatever spring is actually got extended will try to get compressed again. So for getting compressed again, it will try to move in this direction with a speed or with a velocity v. Due to this movement, it will attain a kinetic energy. So when we are stretching it, it will have potential energy, and when we will remove the stretcher, we will simply free the spring, it will retrace its path, gaining kinetic energy due to virtue of its motion. Sum of kinetic and potential energies is thus conserved. So the amount of potential energy is converted into kinetic energy, and in the opposite case, vice versa will happen. Kinetic energy will be converted into the potential energy. Forces of this kind are called conservative forces. The forces where our law of conservation works are called conservative forces. Force where law of conservation follows. Okay. So example of such forces is spring force and the gravitational force. In the spring force, you have seen, like, if the spring is stretched, it will have some potential energy, and when the spring is left, it will start gaining some velocity, and with the virtue of that velocity, it will have some kinetic energy in it. Now that kinetic energy, from where does that kinetic energy came? It didn't came from outside. It came from the potential energy the spring gained already. The potential energy which was gained by the spring already got resulted into the kinetic energy when the spring came in motion. So this is one example. The other example is with respect to electrostatics. With respect to electrostatics is the Coulomb's force between the two stationary charges. Now why we are defining the Coulomb's force here? See, Coulomb's force is anomalous, like it is anomalous to the gravitational force. We write Coulomb's force as K into Q1 Q2 upon R square, and for gravitational force we write G M1 M2 upon R square. So here we take the charges under consideration, and here we take masses under consideration. Coulomb's force is also inversely, like, proportional to the square of the distance between the two charges. Similarly, our gravitational force also show inverse square law relationship, which is that inverse square law. Now defining electrostatic potential energy of a charge in an electrostatic field. How this particular charge gains electrostatic potential. So for the gravitational force, we are able to define the potential energy. Similarly, if we see Coulomb's force, what happens is that Coulomb's force is also similar to the gravitational force. Hence we can define electrostatic potential for the Coulomb's law. It can be defined. Now consider an electrostatic field E due to some charge configuration. Consider the field E due to charge Q placed at the origin. Now first of all, we have to take a system where there are electric field lines. Okay, we have got a system. So we have some charge capital Q which we have placed at the origin. Why we have placed at the origin? We have to take some reference for measuring the distance. So we have taken the distance to be 0 at the origin. It is easiest to calculate any distance from the origin. That's why we are taking origin. And most of the cases we will aim at keeping our charge at origins. Okay, there is no other significance. Only the significance is that at origin we are taking this as a reference of our own mood, and from this 0, calculation of any point is easiest. We do not need to add or subtract any numeral value. Moving on, imagine that we bring a test charge Q from the point R to point P against the repulsive forces on it due to charge Q. Now this is our charge Q. This is our charge Q. This charge Q will have some force of attraction for the opposite polarity charge and some force of repulsion for the like oppositely similar polarity charge. Like if we consider capital Q is a positive charge, it will show attraction for negative charge, whereas if it is positive it will show repulsion for a positive charge. So we are considering this as a charge and this is also a charge small q. This small q was previously at position R. From R we are dragging it to the point P. See, both are positive in nature, so this charge, when it will start moving towards this Q, what will happen is that Q will repel it. Q will repel small q, because both have the polarity of positive charge. It will start repelling. So what we are doing is that though the charges are being repelled, we still aim at bringing these charges near. Okay, so what we are doing, we are working against the repulsive force. Working against the repulsive force. Against the repulsive forces to bring Q, which is positive in nature, from point R to point P towards Q, which is again positive in nature. Okay, so what we are doing, we are working against. So whenever we will deal the symbol of the work in this concept, we will take work as a negative value. So what we have taken is, see, let us take capital Q and small q greater than 0. What does greater than 0 implies? That our capital Q as well as small q both are positive in polarity. Hence they will show what? Repulsion. That's actually of no debate. Now we assume that the test charge small q is so small that it does not disturb the original configuration, namely the charge capital Q at the origin. Now we are making this small q to be an extremely small charge. Now see, we are having a very big ball and a very small ball. So with the help of this small ball, we are hitting the big ball. What will happen? There will not be any changes in the big ball. The this big ball will not start moving ahead, or there will not be any other drastic changes. So that's why we are taking this as a very small charge. So when this charge is coming near to the capital charge, the configuration, the electric field configuration of capital Q charge will not be distorted. It will be same. If there is another charge present over here, will feel the same amount of electric forces due to capital Q as it was observed by this particular charge. Okay, that's why we are taking, so that there will not be any such changes. So we are taking our test charge to be very small. This can be known as test charge. Why this can be known as test charge? With the help of this q, small q, we are trying to test the electric potential of capital Q charge. That's why we are trying to make a test. We are trying to know the values of something. That's why this small charge is known as a test charge too. So what we are doing, that we assume our charge to be small, and hence any kind of configuration of Q is not being getting disturbed or distorted. Now 2, in bringing the charge Q from R to P, we apply an external force F external just enough to counter the repulsive electric forces Fe. So F external is having same magnitude as that of forces due to the electric power of our capital Q charge, but only the magnitude is different. How the magnitude is different? This particular charge is applying force of electric field in this direction, and we are bringing the charge from here. So F external, our force, which the force we are providing, the external force is coming from R to P direction. Okay, from R to P direction. This means there is no net force on the acceleration of the charge Q when it is brought from R to P, that is brought with infinitesimal slow constant speed. One more important concept over here is that the acceleration of charge small q is negligible. It's negligible, or we can say it is zero. Why? Because we are bringing the charge from R to P with a very slow speed. There is no acceleration at all. Why so? If acceleration is increasing, we need to increase the external force also. So we cannot increase the external force. We are having only these limited resources, we can think it in this way, and we cannot increase the external force. Hence we aim at bringing the small q very slowly from R to P, so that there is no acceleration. In this situation, work done by the external force is the negative of the work done by the electric force. Electric force will do its work and external force will do its work. What is the difference in these two work done? Difference is that external forces work done will be negative as it is going against, and electric field as it is going alone will have a positive work done and gets fully stored in the form of potential energy of the charge small q. These two work done gets fully stored, like there is no dissipation and no role of efficiency, giving 100% of efficiency are stored in the charges potential energy form. Charges potential energy form. If the external force is removed on reaching P, the electric force will take charge away from Q. The stored energy potential energy at P is used to provide kinetic energy to the charge small q in such a way that sum of kinetic and potential energy is conserved. Now see this example of the spring. In the case of spring, what we have seen is that when the spring is attached with some mass, the spring gets elongated or it gets extended due to this mass. Okay. Similar way, our charge is placed over here, the capital Q, and this small q is being brought from here to here. So it is kind of a spring. We have just simply like stretched it from R to P. Now this our charge is present over here, Q is present here. So as soon as this force, external force is removed, there is no external force which is holding our small q here, is like this is removed. What will happen? These two will show repulsion. These two will show repulsion. As this is a big charge, capital Q is a big charge, will not move anywhere, but this small q is a very small charge, like with negligible mass. It will aim at moving away from the capital Q charge. So this is called retracing. Okay. In case the F external is removed, it will start retracing its path and will start moving away. When it is like moving away, what will it gain? It will gain some velocity, some speed. Okay, due to this speed or velocity, what will happen is that it will start gaining kinetic energy. Again, this kinetic energy is actually been produced due to the potential energy which is stored by the small q charge when it is brought from the point R to point P by the external force. So this potential energy of small q is changed into kinetic energy of small q, and the amount of energy, overall energy, is same. So what happened is that our energy is conserved. Our energy is conserved. So in this case also our kinetic as well as our potential energy is conserved. Now we will define the work done here. Thus the work done by the external force in moving the charge small q from R to P, from this is R position, this is P position. Initially our small q was here, and after using the external force our small q comes here. After using the external force our small q comes here, and this is our capital Q. So it is brought here. Now we have done some work. You are writing the notes, you are making the notes, listening to my class. This is also a work done. Similarly, when charge is moving from here to here, there is again a work done, and that work done is defined by the force that is provided to the small q charge. Okay, what basically work done is? Work done is defined as force into displacement. So what kind of quantity work done is? Work done is a vector quantity, because force is a vector, displacement is a vector, so why not work done? Hence work done is also a vector quantity. Now this work done in bringing small q from R to P equals to integrated from the distance R to P into F external into the displacement, F external into the displacement. Now this work done is taken negative because we brought Q against the electric force. Hence this is negative. This work done against the electrostatic repulsive force and gets stored as potential energy. This work done is getting stored as potential energy. At every point in electric field, a particle with charge q possesses certain electrostatic potential energy. This work done increases its potential energy by an amount equal to the potential energy difference between the points R and P. Like any point at some rest will have kinetic energy? No, it will not have kinetic energy because it is at rest. V is 0. Kinetic energy is defined as half mv square. So it will not have any kinetic energy. So what sort of energy will it have? It will have potential energy. Energy due to virtue of its position. They will have potential energy. So it is containing, this small q charge is containing some potential energy, but when it is moved from point R to point P, it again gets some potential energy in moving from R to P, and some potential energy at rest. So the total potential energy is given as potential energy present at R point plus potential energy present at P point. So this is the total, but what is the amount of potential energy that is stored during this phase? That will be given as UR minus UP. Now the potential energy difference, that's how we will define the potential energy difference. It is defined as del U equals to del P minus del R, which gives us WRP. So here we have taken UP minus URY because we have seen in the previous equation that work done from R to P is negative. To remove this negative sign, we have interchanged these energies. Otherwise, we will take it as UR minus UP. Now, electric potential energy difference between 2 points. The work required to be done by an external force in moving without acceleration of charge q from one point to another for electric field of any arbitrary charge configuration is potential energy difference, del U, that is defined as work done in moving an external charge q with the help of external force but condition is without acceleration from point R to P, or we can write from any point in space to another point. The potential can be defined for any point in that given definite volume, another point. If we are simply aiming at this, we are having a charge q over here, and instead of position R, our test charge is present at position T. Now, won't it give us the potential energy needed? This is not the case. Still it will give us from any point in the universe which comes along this point, because we need to define for this. So our charge should come in vicinity of this point. So once it is coming to this point, we can define the potential for it. Now few important comments with respect to our electric potential. Above equation depends only on initial and final position of the charge. What does initial and final position of the charge implies is that path independent. What here means is that our charge is present over this point and our plus charge is present over this point. Now this charge wants to roam around. It will go like this. Okay, and now it will come to point P. Now this charge wants to come straight. It will come to point P. Now this charge want to go a long way. Now want to dip. Now again came to point P. In these all the path followed 1, 2, 3. At a point, if we want to see at this point, the potential at this point, and this point, potential will be same. Work done will be same. Now at this point, this and this, again potential and the work done will be same. So it does not matter how the small q charge is coming to point P. It can go around the world and can come to point P, or it can directly come to the point P. In the same, like in both the cases, potential energy and the work done will be same. They do not depend upon the initial and final position of the charge or path followed by the charge. It means that the work done by the electrostatic field in moving a charge from one point to another depends on the initial and final position and is independent of path taken. It is independent of path taken. Fundamental for the conservative forces. It is extremely fundamental. That's why, because we are not taking consideration of all these path followed, we are only taking the concept of initial position and final position. Therefore, we can define these forces as conservative forces. Now, path independence of work done by electrostatic field can be proved using Coulomb's law. This path independence, how these are path independent, can be shown by the Coulomb's law. Coulomb's law is actually proportional to 1 by r square. It is not proportional to the distance covered anyhow, only the distance, the straight line, considering the displacement which we say na, it is only dependent upon that. Now above equation defines potential energy difference in terms of physically meaningful quantity, that is work done. It is very much tough to see the energy. We can feel the energy, but the work done can be seen. Work done can be seen, can be observed. So it is a physically significant, physically meaningful quantity. So we can define this potential energy with the physically meaningful quantity such as work for electrostatic forces as well as all the other conservative forces. We can always add an arbitrary constant alpha to potential energy at every point, since this will not change the potential energy difference. If we are adding the arbitrary constant here and there, it will make no difference. It will make no difference. Then why we are adding? We are just adding to define the this particular point is actually with respect to the path independency. So in the path there can be little less or little more potential energy when it is going from here to there, but overall the change, the work done, the change of potential energy which gives work done is constant always. We have freedom to choose the point where potential energy is zero. We can actually consider a point in this particular line, in this particular distance from P to R, where the field line should be zero. So we will arrange our charges in such a way that the potential over this point will come as zero. So we have this freedom. Then when electrostatic potential energy is zero, so we aim at at infinity from this q charge. We are dealing somewhere here very far at infinity. So at infinity, what will be the potential energy difference? How we can give the potential energy difference? Potential energy at infinity will be denoted by U infinity, that is potential energy at infinity, and potential energy at P will be UP. So work done to bring our test charge Q from infinity to point P is W infinity P equals to UP minus U infinity, which gives us UP, because U infinity we can take as 0. Above equation defines potential energy of charge small q at a point in the presence of field due to any charge configuration is the work done by the external force equal and opposite to the electric force in bringing the charge q from the infinity to that point. So this equation, this particular equation, see I am marking in red, this equation explains us a situation where the test charge is brought from infinity to point P and we defined work to bring charge from infinity to point P. So this is all for the today's class. This is the introduction to the electric potential and how this electric potential is calculated. We will just summarize our class here and then we will see the other concepts in the next class. Let's know what we have read in today's class. Okay? Today's class. So what we have understood that we are going to read about electrostatic potential. Electrostatic potential. So it is the energy which is stored by the charge when it is at a given position. In simple words, okay, it is not the exact definition, but it is to understand in the simple words. Energy stored by a charge q at a given position, Now we know that the total energy is given as total energy of any system, total energy equals to potential energy plus kinetic energy. So this, if there is decrease in this energy, this will increase, and if this energy is increasing, this will start decreasing. So overall what will happen, this will remain same. So how did we concluded this thing? We concluded this due to the law of conservation of energy, law of conservation of energy. So if energy is being conserved, any force will show this kind of energy, that force is known as conservative force. Conservative force. So the conservative forces are spring force we read in 11th. Then second is gravitational force, again we read in 11th. And the third one is Coulomb's force, and this is read in our previous chapter, right? Now this Coulomb's force is given as F equals to K Q1 Q2 upon R square, whereas our gravitational force is given as Fg equals to G into m1 m2 divided by R square. So these two show similar formula. So we can define potential for the gravitational force. So as these two forces are similar, they show inverse square law relation, we aim at defining potential for the electric charges also. So we have taken consideration that this is our positive big Q, big charge, and at a distance of R, at Q, R plus capital R, we will take Q, R, this is Q, our Q, this is our small charge, Now this small charge is moving, is brought near the capital charge at a point P. To bring it from R to P, we have applied some external force F external. So this is positive, that's why the force due to electric field of capital Q will be equal and opposite to external force. The work done to bring the charge from R to P will be given as work Rp equals to R to P F external into dr. As the work done is negative because it is against the repulsive force, it will be external into dr. Here R and force both are vector quantities. Now the potential energy is given as the energy difference at P and R. Energy difference at P and R. So del U equals to del R minus del P, which will give us minus of WRP, or UP minus UR will give us WRP. So here what is the difference? Difference is negative is removed. Negative charge or negative mark is removed. So this is the difference here. So this is how we give the difference of potential from this point to this point. Why we need to find the difference? Because initially charge will have its own potential energy. By doing this subtraction, we have eradicated that option, eradicated self energy. We are only describing the energy possessed due to the force external provided to the charge. So here these are the formulas we have read, these are the relations which you need to make note of. So that's all for today's class. We'll meet in the next class with a new concept of the electrostatics. Bye bye, have a good day.